Well, as promised, we're going to continue drawing rational curves. This one's a little bit different. Here is the drawing. Can you possibly come up with a rational function that matches it? So there's not going to be like a guaranteed correct answer, but we can be kind of reasonable about it. For example, it's got a vertical asymptote at x equals -4 of odd multiplicity because it did opposite behavior on opposite sides. Similarly, this is a vertical asymptote, but of even multiplicity. It has a horizontal asymptote of y equals 1. That tells you a lot. Okay, that tells you the numerator and denominator are of the same degree with the same leading coefficient. Also, it appears to have a root at -1, specifically of even degree, and a root at 3 of odd degree. And we have an intercept of 0, -1. That's more information for us. And we never cross the horizontal asymptote. That's a lot of information to have. So there's no unique solution here, but let's piece it together. Okay. Once it's in lowest terms, we can find intercepts here. Okay. So we know that the numerator, we're only looking for now at, where'd my pen go? There it is. We're only looking at the numerator. It has a root at -1 of even multiplicity and at 3 of odd multiplicity. So the simplest thing we could do would just be x plus 1 squared times x minus 3. We have no reason to make it more complicated if we don't have to. This matches the fact that we have a root of even multiplicity at -1 and of odd multiplicity at x equals 3. So next, let's look at the vertical asymptotes. We have a vertical asymptote of odd multiplicity at x equals -4, and a vertical asymptote of even multiplicity at x equals 2, which I just note by saying it flipped or it didn't. So similarly, odd multiplicity at -4, even multiplicity at 2, this is the simplest thing I could throw together for the denominator, q of x. So this is a reasonable candidate for the function. Okay. What would the horizontal asymptote be? Well, if you expand all of this out, you end up with an x cubed and then lower terms. And here you get an x cubed and then lower terms. So yeah, this already matches that the degree of the numerator is the same as the degree of the denominator, with leading coefficients being equal to each other. So this is fine. Okay, so we don't actually have to do any adjustment. If the horizontal asymptote was y equals 2, I might want to throw a 2 out in front. If the horizontal asymptote was, -1/2, I might want to throw a -1/2 in there. But the horizontal asymptote is just 1, so we're just multiplying by 1, so don't worry about it. If you graph this, it looks pretty correct right now. So sorry, I'm just going back to their picture here, because there is some information. This intercept, it appears that if you plug in x equals 0, you should get out y equals -1. And let's just check. What is r of 0? We're going to get 1 squared times -3 over 4 times -2 squared. This is -3 over 16. So I don't think we quite matched that intercept. Matching this intercept would be difficult. You don't just get to, for example, do a plus or minus some number here. That's going to really throw you off. You want it to look just like this. And if what you tried to do instead to fix that up would be, let's try to change the intercept by like subtracting 7/16 or whatever was missing here. Now the roots of this have changed. If I set this equal to 0, it's not just going to be a -1 and 3, because this is going to throw everything off. Matching that intercept is actually a much trickier proposition, which is probably why the book omitted it, thinking we wouldn't notice. So this function probably is not what actually produced this graph, but it does at least match the roots, horizontal and vertical asymptote appropriately. It just doesn't seem to match one of the intercepts. Okay. On to the next example. We've got a metal company. We manufacture cans. Awesome. Why not? They're cylinders, as they tend to be, with a capacity of 650 milliliters. A cubic centimeter is a milliliter. The top and bottom of the can are made with a special aluminum that costs 6 cents per square centimeter. But the sides are a bit cheaper. They're made out of 3 cents per square centimeter. This is reasonable. On aluminum cans, the side is actually generally thinner than the top and the bottom. The top and the bottom have to hold, well, the bottom isn't flat, first of all. The bottom tends to have a curve in it. The top has this like special pull tab shape. It also is where you seal it up. So there's some extra cost associated there. So sure. So the side, if I had this cylinder of radius r and of height h, the top is just the circle of radius r. Its area is pi r squared, but the bottom is also of area pi r squared. The side, if you imagine cutting this and then unrolling it, is a rectangle whose height is just the height of the cylinder, but whose width is the circumference of the cylinder, which is 2 pi r. So the area of the side is circumference, which is 2 pi r, times the height, which is h. So this top costs 6 cents. The bottom costs 6 cents per area. And the side costs 3 cents per area. So can you express the cost of the material as a function of the radius? Graph it, find the value of r that has the smallest cost. So I'll just come back here to remind you of this geometric picture and what the relevant costs are. It appears I have r and h as variables. Spoiler alert, the volume has to be 650 milliliters, so they're not really both variables. So try to find r as the only variable and then solve this problem. So the first thing you need to do is solve for what h is. Okay, so notice, well, we'll do the cost involving h, and then we'll substitute that in later. So the cost is just the cost of the top plus the cost of the bottom plus the cost of the side. The top and the bottom are both pi r squared at a cost of 6 cents. The side is an area of 2 pi r h at a cost of 3 cents. So add those up. This simplifies to 0.12 pi r squared, 0.06 pi r squared h. So sorry, pi r h. But I don't want h to be its own variable. Okay, but the volume of a cylinder is pi r squared h. It's the area of the base. Whoops. It's the area of the base times the height. And we know that's supposed to be 650. So use that information. Gives me h must be 650 over pi r squared. So if I go back to our original cost function, the original cost function looked like it depended on both radius and height, and it was 0.12 pi r squared plus 0.06 pi r h. I'm just taking value of h and substituting it in. Observe that this pi is going to cancel, and one of the factors of r is going to cancel. 650 times 0.06 is just 39. So what we have is 0.12 pi r squared plus 39 over r. This is a rational function. What you should always get in the habit of doing with rational functions, notice it looks like, oh, I have a quadratic plus rational function. No, if you give it a common denominator, which you should really be in the habit of doing when dealing with these things, I want to give, let me clear out my marks so I can be a little more precise here. The common denominator is just r. So 0.12 pi r squared, I want it to have denominator r, but if I'm dividing by r, I'd better multiply by r as well. And that's why we have an r cubed here. So now I have a nice rational function. Notice this is a polynomial of degree 3 over a polynomial of degree 1. It's a rational function representing my cost. And if you graph it, you end up with this. And the next part of the problem said find the minimum. Okay, you kind of need a calculator or a computer software to do that. So using this as your cost function, find the minimum. So it's at about 3.73, 3.759 dot dot dot. Yeah, I'd round that off. 2 decimal points is almost always enough. 3.73 centimeters. If I make that the corresponding radius, what is the cost? Plug it into the formula and you'll get 15.7 cents. So a cost of 15.7 cents per can in order to make our 650 milliliter cans. Your typical soda can, your 12 fluid ounce is like 300 and something milliliters, so this is a fairly large can. Okay, so that ends this section. That is section 4.4, I want to say. So come on back next time for section 4.5. And really, 4.5 is a lot of work, I'm not going to lie. Okay? And it's all in the service of one question. The first step in graphing and understanding a rational function is, can you factor it? Can you find all of its zeros? The next section is all about, how do I find the zeros of a polynomial? Okay, if it's of degree 2, we have the quadratic formula. What if it's not? So make sure that you are rested and ready to focus. The next section, 4.5, tends to be one that can throw people for a loop.